All right. Welcome, everyone. Thanks for joining. My name is Nick Lee. I'm a partner tech lead at Labelbox, and I'm excited to be sharing the stage here with my friend Dexter from EPRI.
Hi, everyone. Good afternoon. I'm a principal technical leader with EPRI. We're an electric power research institute. We conduct research for electric utilities, and my domain of expertise is in inspections. Nice to meet you.
And today we'll be diving into how EPRI uses computer vision to mitigate wildfire risks for electric utilities. So to kick things off, I just want to give you a quick overview of Labelbox. Labelbox provides an easy way for data teams to discover and organize their unstructured data on their data lake. So teams who need to work on AI problems that require complicated data types like images, video, and text can easily browse their data lake, create these data sets, and set them up for AI projects. The platform itself allows you to handle a variety of formats, including geospatial data, audio files, and even some industry-specific formats like DICOM. And you can easily onboard your third-party labeling teams or in-house experts to label these images and other assets, or you can connect your machine learning models to the platform and do a model-assisted labeling workflow. But that's all I'll say about Labelbox for now. I want to hand the stage over to Dexter to talk about some of the amazing work they've done at EPRI.
Thank you, Nick. So as I started mentioning EPRI, we're most of you've probably never heard of us before. Our typical customer base are electric utilities. And really what we try to do is help them identify technologies to improve their traditional processes, whether they're advancements in safety, advancements in the energy creation itself, clean energy, and also things that are facing towards the consumer. So how do you keep energy prices down? And lastly, how do you maintain a very high reliability? I would say that at least in the States here, we probably take it for granted that when we plug in a phone charger into the wall, that there's going to be electricity there. This industry kind of prides itself on 4 nines of reliability. And that being the case, though, we're always looking for incremental improvements. So our role in this domain is to really identify gaps, identify opportunities where there's interest for utilities, and basically work collaboratively. At the end of the day, utilities are regulated monopolies, so there's not as much competition as probably some of you between one another out there. They all kind of manage similar infrastructure. Poles and wires in Alabama, where I'm from, look like poles and wires in California. So typically there's an opportunity to identify projects, technology evaluations, or just new ways of sharing information, and you can work collaboratively with peer utilities to kind of fund that project. And really that's how EPRI is a sustainable business model. So my area of research, even though EPRI covers everything from the generation of the electricity to the consumption, my work is in the poles and wires environment, so the overhead transmission and distribution lines. Specifically, I work in a domain of inspections, trying to find technologies to do inspections better, safer, faster. And the motivation for that, you don't have to be a subject matter expert to understand this, but electricity outages are anywhere from an inconvenience to a major catastrophe. So the electric utility here is Pacific Gas and Electric. Back in 2018, they had a insulator failure that resulted in the Camp Fire. Several acres burned and people lost their lives. So it's a really big deal. And if you think about, again, the motivation here, really what we're trying to do is see, is there better ways of performing this work? Utilities know that outages can be catastrophic. They know that when energized conductors hit the ground, there can be an ignition source. But at the end of the day, it's just a really difficult problem to manage infrastructure that is spread out over thousands and millions of miles. And understanding that just the smallest little of defect on some of these structures that are built to last 30, 40, 50 plus years can result in a catastrophic failure. So you'll hear me use terms like distribution or transmission. Really, it's the same thing. It's overhead energized conductors. The mainly difference is the size, the amount of power transfer, and really the voltage that separates them. But to give you an idea of just how big of a problem this is, in the United States, they estimate there's about 200,000 miles of transmission. And a lot of this is typically very rural, hard to get to, hard to access. The traditional inspection models that utilities have deployed has been helicopter-based. You have people riding in the helicopter, getting close to the infrastructure, doing a visual inspection. That by itself has safety concerns. There's about a fatality a year related to helicopter collisions with transmission lines. Now, the other domain is distribution, and distribution is much longer in terms of the total amount. There's about 5.5 million miles of distribution in the United States, and typically this has been run-to-failure infrastructure, mainly because, again, there's just so much of it to actually get out there and inspect, and typically your amount of customers that may be behind some of these devices don't justify an inspection program to stop issues before they happen. But if you recognize how important it is to mitigate some of these wildfire scenarios and some of these high-risk environments, that run-to-failure mentality no longer applies. So what we're trying to do is help our utilities identify new ways to perform this work. What you'll see on the left is a video of a drone doing an autonomous flight around this structure, maneuvering in and out of the conductors, capturing imagery on this one capacitor bank pole. The idea is, again, if you can automate the flight plan, you can perform this task safer, faster, to a consistent level of quality than even a human inspector. This flight on the left took about 2 minutes, again, fully autonomous, and it captured about 48 photos. What we're trying to do on the right is, again, automate the data that's collected and the review of that data to identify issues and then be proactive about fixing them, again, before you have a catastrophic event. Both of these technologies show promise, but a full solution of autonomous data capture and autonomous data interpretation just does not exist today. And the problem, or the reason why, or one hypothesis, is that it's just a very difficult problem, to be frank with you. There are so many different types of objects of interest. All of those objects of interest degrade and fail in different ways. And at the end of the day, just as an industry, we don't have the data sets historically to build some of these models. A good exercise to kind of prove this point is if you go to open images that Google manages or ImageNet and you type in transformer or insulator or pole, you're not going to get any results. Again, these data sets haven't existed. The advancement of drones is kind of changing that. And what I'm trying to do is convince my utility members that there is value in collaborating among themselves for data sharing, as well as collaborating with a community of data scientists and engineers like yourself. So, to that point, we're trying to fill this gap. I acknowledge that this is, again, a monumental task, but you've got to kind of take a step to almost prime the pump, if you would. We've labeled, I guess, close to 50,000 images for both transmission and distribution, with the idea of putting these in the private, public, and academic sector to support commercial development or just academic research. A little bit about how we did this. You got to start with the data, I suppose. And as it relates to our task, it's inspection imagery. Now, getting this data from utilities is kind of difficult. Utilities, and there's a lot of lawyers that work at utilities, to be honest with you, and they don't want to be extremely transparent with sharing something that's going to put them at risk. So what we try to do is show them ways to clean and anonymize the data through either pixel obscuration, removing people's faces, just like Google Street View, to geospatial information translation, so like moving the information that's in the metadata into the ocean. The other thing that we did, not only cleaning the data and preparing it, but also we wanted to leverage Labelbox's workforce to basically try to label as much data as we could for the budget that we had. In other words, we're trying to see, can we use non-utility subject matter experts to go in and annotate these images under some guidance that was developed by subject matter experts. In order to do that, in short, again, we partnered with Labelbox. We spent about 3,500 non-subject matter experts on this annotation task, and about 200 hours of my time and a colleague's time to kind of manage that activity. We stored our images in our Azure container, our cloud, and then would just render those images using Labelbox's software. I thought this workflow worked fairly well, and really what I'm trying to do is share these data so that innovation can begin with them. To that point, we've put these data sets on Kaggle. One of them is the foundation data sets for an object detection competition, and the other one is just a standalone data set. So again, imagery that is near impossible to go and get by yourself, I suppose. I guess you could fly a drone and operate it around a power line. It's just generally not recommended. But we've created those data sets and are really just hoping we're going to leave this competition open for about 3 months. We're announcing it today, so a little bit of I hope good news, I hope, for those that are interested in this. And we'll talk more about these and give you some QR codes if you want to go and grab these links instead of having to memorize them. So let me turn it over to my colleague, Nick, and he's going to show you a little bit about some of the labeling workflow and the Databricks architecture.
Awesome. Thanks, Dexter, for the great overview. As you saw with Dexter's example, a lot of large-scale AI projects require massive scale data collection, handling, annotation, and very big workflows like that. And today I wanted to dive into the Databricks Lakehouse and look at how we can improve some of the workflow related to data collection and labeling for AI. So Labelbox and Databricks have partnered to bring an end-to-end solution for different parts of the AI development stack, starting with data labeling and management within the Labelbox platform, and then leveraging the power of Databricks compute for model training and model deployment. The Labelbox connector for Databricks helps facilitate the flow of data. You can easily queue your unstructured data from the comfort of from the comfort of Databricks into Labelbox for labeling. Once it's labeled, get your annotations back into Databricks as a Spark table, where then you can run your model training on that. All right, so Dexter, you showed us a lot today about your project, and I was curious if you could comment on the process you used to get all of those images, thousands and thousands of images from your drones into a platform like Labelbox, and then eventually, to your model training environment. But let's focus on that data flow. How did you get all of those assets?
So Nick cued me with this question before, but I'll just summarize it by saying it was a pain in the ass. We have internal shared networks with permissions-based. We sometimes get data out of projects that we run or data that's given to us from electric utilities. Those will have, again, different permissions and licensing. We're pretty much, it's really embarrassing, to be honest, but it's a file folder structure with an Excel spreadsheet of this folder contains information related to this data set that came from this location, and here's the permissions that go along with it. It's very manually intensive, is what I would say, and open for duplication of data sets as well.
That makes sense. And this is actually a really common pattern that we see. A lot of teams just get started with batch processing of images, and this is viable up until a certain point. But once you start achieving massive scale, batch can only take you so far, and your time is really valuable. So we'd rather have you working on hard problems and not manually moving folders, from one drive to another, right? So once teams require larger scale flows of data, they often we'll think about, well, let's stand up a notification service and build an application that will listen for new files or new images as they come in from our drone fleet or something like that. Or maybe they'll stand up an orchestration system like Airflow and listen for new assets as they flow into their bucket. But all of these are kind of heavy lifts for just the simple function of getting your data from over there into your Lakehouse and into your labeling platform. And today I want to show you an alternative way that takes advantage of the tools that we already have, so we don't have to worry about all that overhead of standing up other applications and maintaining that infrastructure. Okay, so what I'm proposing today is taking advantage of our compute environment, Databricks, and using Autoloader to automatically listen for new assets as they land in cloud storage and move those assets over to Labelbox for labeling, and then exploit the Labelbox connector for Databricks to get those annotations back. So this architecture is a lot simpler than standing up all of those other tools just to monitor that bucket location. And hopefully today you'll see that it's a lot simpler to set up. So let's dive into Databricks and get this started. Okay, so right now in Labelbox, I have an empty data set called drone survey images. And what we want to do is get some initial images over there for labeling from our S3 bucket. I've currently mounted my bucket in Databricks. And so all I'm doing is identifying that empty data set in Labelbox. And then I'm going to define a pandas UDF that I will attach to Autoloader to process those files as they land in S3. So these functions I have here are actually pretty simple. I'm just creating a virtual hosted URL based on my S3 region and bucket name. I'm taking a file path from DBFS and translating that to the S3 URL, and then communicating with Labelbox and sending those URLs. So a key point here is your image actually stays in S3. It never is copied over to Labelbox, and that way you don't replicate your data in your data lake, and you have the security of your bucket storage. You don't have to worry about copying it out. So I'm going to queue up those functions there, and then now we can define our streaming data frame. So what I'm going to do is use spark.readstream, specify that I'm looking for cloud files of the JPEG image type, and then I'm going to compose my select statement on that data frame, and that's where I'm injecting my pandas UDF there that will pass the URLs over to Labelbox. So really, all this took was the initial definition of what information we're trying to pass to Labelbox, and then just over a dozen lines of code to set up that streaming job. And once I kick off that stream, Autoloader will initially look into that S3 bucket, realize that none of those images have been sent over yet, and then queue that up for labeling in Labelbox. So we can actually go take a look at the project in Labelbox. I'm going to visit my Partner Connect portal here, sign into Labelbox through Databricks Partner Connect, hop over to my catalog pane, and there is my drone survey images data set with those initial 5, in this case, images from my S3 bucket. So now that I've got those 5 in there, I can actually show you what a labeler might see. These are in Dexter's example, technicians in the field coming in here and annotating these assets. Right, so the data set has been created in Labelbox. We have a project here with an ontology. In this case, I'm asking to annotate the poles, wires, insulators, and crossarms. So Labelbox itself is a very easy to use web interface here where you can really annotate at the speed of thought. Just using my mouse and keyboard here, very easy to bring in non-technical subject matter experts to any format that you like, get that labeled, and then move on to the next asset. In the background, Labelbox has a queue manager that is distributing all the work to any labelers on your project, so you don't have to worry about the same person, or excuse me, the group of people working on the same image. We'll automatically make sure people aren't overlapping on their work. So let's actually go ahead and finish this one annotation here, just really quick. Let's draw a bounding box on this cross arm. Resize that. Cool. And then we'll hit submit and move on to the next. Great, so now our team behind the scenes, our hypothetical team, will be labeling these images. Let's see how we can actually get those annotations back into Databricks. So we call the Labelbox Connector for Databricks, providing the project ID from Labelbox. And just with 2 lines, we get all of those annotations that I just dropped here as a Spark table. The money is really in the label column, where you get all of those classifications, objects in a neat array, coordinates of the bounding boxes. And if you're doing segmentation masks, you'll also get the PNG files that describe the mask on those images. So from there, your data scientists can take that data frame, process it, train models, and you're off to the races. Next, if we want to clean that up, we have some helper methods in the connector that will parse out classifications and objects into their own columns. So it's a little bit more queryable. You can understand it visually, clearly. These images have poles and wires, as well as different image quality here. But for more complicated ontologies, you can build these big tables that are queryable with SQL and just easy to hand over to your data team to work with. So autoloader is still running. Let's say that we had those drones send a new batch of images. So we can actually come in to my S3 bucket. I'll just drag in these additional 10 images here, upload, and without any other manual effort, Databricks autoloader will pass those URLs over to Labelbox. They'll be queued up for labeling and available immediately. So if I come back to my catalog here, you can see my 10 new images just arrived in the data set, and they're queued up for labeling. So stop dealing with folders and manually moving things. Just set it and forget it and have your data flow through the data pipeline for you. Awesome. So next, what I want to talk about is what we can do after we have those annotations in our Lakehouse. Let's say your data scientists trained models on that data. You can actually do a model-assisted labeling workflow where you plug your model back into Labelbox, and you can visualize those predictions on those assets in Labelbox and make corrections. So let's actually dive back into Databricks and see how that looks. Okay, so in this example, I'm just providing 3 files to a model that has been previously trained on the EPRI dataset. So there are the URLs. I'm just loading them using OpenCV. So let's get a preview here. Looks like your standard power pole with some cross arms and insulators. And this is the model file that one of the data scientists from EPRI sent over to me. So I'm actually just going to load that. It's a YOLO v5 model, so it'll be drawing bounding boxes. And I'm asking the model to make predictions on those 3 images. I've already created a data set in Labelbox before this demo with those 3 images just to save time. So I'm going to load that up and then connect the model predictions to the specific image entry in Labelbox. So that's what I'm doing in this code. I'm just connecting a data row ID from Labelbox to the file name here in Databricks. So you can see the model predictions dropped a bunch of bounding boxes with the X coordinates, and you can see the classification of those objects, as well as the file names. And these data row IDs are Labelbox specific, and they will help us bind those predictions to the correct asset in Labelbox. I'll also save a copy of my predictions as a delta table, just so I have a reference. So if later on I make some changes or improve my model, I can also refer back to my original predictions and do some versioning and understand how my model changes over time. So next, I'll set up a project in Labelbox with the classifications that correspond to what our model had output, so insulators, crossarms, poles, etc. And now this code here is simply mapping those coordinates into a JSON file that Labelbox understands. So any prediction from any model can be mapped into JSON, and we have some helper methods that make that easy so you're not struggling with ETL all the time and like mapping your predictions to specific object types. In this case, I'm creating rectangles and just providing those xmin, ymin, xmax, and ymax coordinates from my initial table. So once my JSON is ready, I run my command here to send those predictions over to Labelbox. And back here in my project view, if I refresh this, I should now have a demo MAL project with those predictions fully visualized. So now my subject matter expert can come in here and say, hey, this model actually did a pretty good job at labeling these cross arms and insulators, but maybe I realize that one of these could be tightened up a little. So I'm going to make a correction. This bounding box is also a little bit off to the side. Maybe it needs to be resized to be perfect for that cross arm. And this pole looks pretty good, but we can always do better, so we can actually tighten that up.
One thing we plan to do after we finish our Kaggle competition is identify some of the better performing models and then go back and relabel some of the images we've already labeled with this model-assisted workflow to have one-to-one comparison metrics between if you went through it without this model-assisted, how long did it take, what was your quality metric, and then redo it with machine-assisted labeling. And really our goal is to try to just present that information back to our utility audience so that they just have a better understanding of this labeling task.
And also to drive home the reason why it's helpful to visualize your predictions at scale like this is you'll notice here that this model actually forgot one of these insulators. So I can easily come in here, drop that bounding box in there, and then on the next training run, hopefully my model will learn from this data and not make the same mistake twice. Okay, so you saw really quickly model-assisted labeling workflow. We don't have time to get into it today, but Labelbox is more than just a data labeling platform. We also have a diagnostics capability that allows you to quickly visualize your model predictions at scale on multiple assets so you can understand where your model needs help and prioritize the next batch of data to maximize your training improvement for the time and effort that you put into labeling all of this. You can also upload your model embeddings to the platform, and that will allow you to look at similar objects through a view like this and identify clusters, hotspots, if you will, where your model may be struggling. And that way, you can then call your data team and say, hey, our model needs help on this particular camera angle or images with this particular lighting. And so you're not trying to label the whole world. You're only focusing on labeling the minimum viable data to get the best performance increase on your next training run.
Yeah, thank you. And I think that calls back a part of the keynote that Andrew Ng said this morning on, a lot of the work is moving into the data itself, not so much the model development. And he also said something else. He said that democratizing AI benefits everyone. And I think, to try to just expand upon that, we're not only democratizing, I suppose, some of the models, but also just the raw data itself. And particularly, these are data that are just very difficult to get in this domain. It's even as a researcher for the electric utility industry, I still struggle to get data from utilities. But I recognize that there is significant private, public, and academic benefit by trying to take these data, take on some of the burden of labeling, and putting them into the public domain for innovation. And so I would encourage you, if you're interested at all in this space, go and check out these Kaggle links on the data sets as well as the competition. And maybe we'll have an interesting case study to tell you about how this workflow works next year.
And also, Labelbox is excited to partner with EPRI on this effort. We are hosting the dataset for free on our platform, so you can actually create a Labelbox trial and browse that dataset totally free, visualize all 300,000 annotations, 35,000 images, and hopefully this supports data scientists who are out there trying to work with this dataset and reduce wildfire risk for electric utilities. There are the QR codes for those data sets and the Kaggle competition. If you want a free trial of the platform, go to labelbox.com, and there's a link for more information on our partnership with Databricks. Thank you, and we'll be happy to take questions.
Thank you. Yeah, so I got a question. What's your end game? What do you hope to get out? Are you hoping to recognize the faulty parts on the power lines, and do you have the faulty parts labeled as faulty? So what would be successful? I'm guessing the competition is to train a model to label other images.
Really, the value I think that can come from putting this labeled data set in the public domain is really threefold. One, this evaluation of model-assisted labeling as a case study with hard metrics between manual labeling versus this assisted approach. The other one is the first step in that post-inspection workflow of object identification and then subclassification of, do I see an insulator, yes or no? Okay, now is the insulator defective, yes or no? We didn't embed that information within this data set because we just don't have it. We don't have a large repository of defects. But ultimately, it's defect recognition and also prioritization. Is this worth fixing today versus tomorrow? So that is a long-term benefit, but this data set's not going to solve that for our industry. The last thing is onboard decision-making for these inspection technologies themselves. So can you embed some of this intelligence on the edge, on the aircraft, on the drone, to help make a decision of, do you see the insulator, yes or no? Do you see the crossarm? If you see those two things, there's a connection point right there that has to be viewed from 3 different angles. So the idea is if I can take these data sets, take on the burden of labeling it and sharing it, I can come back around and test more sophisticated inspection technologies on both the data capture, the data labeling, and then the post-inspection workflow. I went down the road of trying to label every single thing that's of interest in these images, but that's an almost boiling the ocean approach, and it can get you into this analysis paralysis. So I thought that while I'm only labeling a few classes here, there's still significant value in just putting the data out in the public domain. So we're not really building models, and we're not in the market to commercialize. We're a nonprofit. I'm really just trying to test inspection solutions that don't exist yet by filling this data gap and allowing innovation to happen.
Thank you so much for the presentation. Do you think that in terms of defining the problem, right now it seems that we are focusing on object detection. Do you think that reconstruction, 3D shape of the poles could also be helpful?
Yeah. Some of these more sophisticated drone approaches will do a V-slam. It will identify the shape of the object stereoscopically through the structure from motion, all that stuff. If you could do that on board the aircraft and have an understanding of that structure configuration and then make a navigation decision of, okay, go to this point and capture this image how we're defining it. Really our goal here is try to optimize, reduce the number of time per structure and reduce the number of images. So there's a lot of different approaches. I think photogrammetric or structure from motion workflows certainly are worth investigating. I don't know that they're the end solution. Did I answer your question or did I ramble about something? I sometimes do that. I'm sorry.
Okay, so we actually ran out of time, and let's give a round of applause to Nick and Dexter.